Well, good afternoon, everyone. I'm Chris Fanta. It's my pleasure to welcome you to Asthma Grand Rounds, the new season. And we have a wonderful series of presentations planned throughout the year. I hope you'll look at the schedule, make note in your calendars, and come join us for all of them. And I also welcome those who are joining us by live webcasting. Thanks for being here, and you'll have the opportunity to submit questions to our speaker at the end electronically. So we're delighted to have for our first presentation of this season Dr. Xingbin Ai, who's a member of the Pulmonary and Critical Care Division here at the Brigham and Women's Hospital. And she trained in both neurobiology and skeletal muscle development, and then has combined these interests and areas of expertise in her research into innervation of human airways in both development and disease. And so we're very pleased to have her here today to speak to us about airway smooth muscle phenotypes in asthma. Dr. Ai. Let's see if we can do this. Good.
I want to thank Dr. Fanta for inviting me, and I have to be the first one to kick off this season. I'm very fortunate to have this opportunity to share our study with the broad asthma research community here at Brigham. So I think some of you may have come to the early medical grand rounds this morning. We had 3 wonderful talks talking about genetic predisposition, the variants in our own genome, how that contributes to pathogenesis of chronic lung disease, such as asthma and COPD. Here I'm going to present you to a second cause, which I think is equally important for these chronic lung diseases, especially asthma. This cause is the environment. So today I'm going to talk about some of the new findings we have, along with the smooth muscle innervation. And I want to convince you towards the end of my talk, asthma is not just an inflammatory disease. It also has an element of neural components in there. So first, I have no disclosure for this meeting. So for this audience, I don't think I need to introduce asthma. Asthma is a major health burden. It's a chronic inflammatory disease. There are a few clinical hallmarks of this disease that include, this includes mucus overproduction in the airway smooth muscle thickening, as well as the reversible airway hyperreactivity. So this is the normal airway with open lumen, where the air can flow in and flow out. Here is the asthmatic airway. You can see not only the smooth muscle is hyperreactive, reduce the lumen size, there is also mucus plug in the airway, blocking the airflow. So it's a major health burden because the number of people affected, as well as the severity of the disease, causes a lot of emergency visit, as well as losing working days, as well as missing school days. One thing I want to emphasize about this disease is, although asthma is known to affect patients of all ages, it is known to be a predominantly childhood disease. So I want to use this study as an example to show you how early life events is heavily impact on the progression of this disease. So this is a work published in 2008. This work is from Dr. Martinez' lab. What they did is they followed 1,246 healthy babies ever since they are born, all the way up to 22 years of age. So amongst these 1,246 individuals, you have healthy individuals all along the life. And you also have a subset of these people who initially develop asthma-like phenotypes. However, they outgrow eventually. And then you also have this group of people who develop chronic asthma. So the y-axis in this graph is the lung function measurement. The x-axis shows the age of the diagnosis of the asthma. So if you pay attention to this middle group, this is the group who eventually outgrow asthma later on. The earlier the diagnosis, the poorer the lung function is, although they don't present asthma-like phenotypes. In addition to the asthma group, the earlier the diagnosis, the poorer the lung function is. So I think I want to show you this study to highlight the key message here. The message is asthma, if you start to treat later on, it's already too late. Whatever happened is already happened during this early life. So it is very important to understand what is happening in this early life and how these early events eventually connect to the abnormal lung function later on. So importantly, the lung doesn't stop. Lung development doesn't stop in uterus. So we're mostly using the mouse models to study this devastating disease. But I do want to highlight there are lots of similarities between mouse lung development and human lung development. So one thing that's in common is there are a lot of postnatal development after birth. In mouse lungs, there's a great deal of vaporization within the first 3 weeks. In human, this happens within the first 3 weeks. The lung development completes in mouse in about 6 weeks, while human, this process lasts up to 18 years of age. So you could probably imagine anything happens during this critical postnatal time window may have profound impact on the lung structure and function. And we believe this may be the key factor that contributes to pathogenesis of chronic lung disease. So as I said, because the lung disease has a strong association with the early events, we decided to take a very different approach from traditional asthma research, which is to use adult mouse models. We believe study the young mouse model and study how this young lung changes along with the environment insult will guide us into how the lung become abnormal later on. So to do that, we generated a new mouse model of childhood asthma. In this particular model, we use ovalbumin, which is a natural allergen for animal. What we did is we sensitized this animal at the postnatal day 5 at the postnatal day 10, followed by 3 aerosolized ovalbumin challenges. And we analyzed mouse at day 21. Remember, this is the day when the lung takes the mature configuration. So we first evaluated mouse at this age to make sure all these parameters of asthma are present. So this is basically you can evaluate the smooth muscle thickening with airway smooth muscle immunostaining. You can evaluate the mucus in the airway by PHS staining. You can measure the inflammation by measuring the key Th2 cytokines, for example, IL-3. And most importantly, we measure the airway reactivity in response to increasing dose of methylcholine. So based on all these parameters, we believe compared to the saline control, which is the PBS here, that mice receive the PBS challenges, this model is working. They present all the key hallmarks of the asthma in patient. So the most striking finding comes when we let this mouse sit in a cage for another 5 weeks. And then we went back to evaluate the airway hyperreactivity again. So just to remind you, at this time, the airway hyperplasia is largely dissolved. However, the mouse still maintains its hyperreactive phenotype in response to methylcholine. So this is the key hallmark of the asthma disease, the airway hyperreactivity. I also wanted to note at this time, the allergic inflammation is also largely dissolved. So this hyperreactivity cannot be caused by the residual inflammation. So to address whether this is unique to this postnatal neonatal window or it applies to all the ages, we did a similar study, this time started with the adult mice. We started with 3-month-old mice. We used a similar challenge and a sensitization regimen to induce asthma-like symptoms. And we analyzed at day 19. So at day 19, these adult mice presented all the hallmarks of asthma, such as mucus metaplasia, smooth muscle thickening, as well as overspecific IgE in the blood, and airway hyperreactivity. However, these phenotypes never last. So what we did here is let these adult mice sitting in a cage for another 2.5 weeks. This is the time when the inflammation is resolved. What we found is IL-13 is also resolved. This is another marker of the inflammation. And then airway smooth muscle lose this hyperresponsiveness. So these striking differences between these two models told us 2 things. The first thing is the neonatal window is very sensitive for perturbation. And the second is this perturbation may be linked to long-term airway dysfunction. So what did this perturbation does to the lung? Because in both models, airway inflammation is resolved at the time during recovery. So we believe the airway inflammation cannot be the cause of these persistent phenotypes only in the neonatal window. Because our lab is very interested in how airway smooth muscle is innervated, we decided we decided to take a look at the nervous system in the lung. So this is the image. We did 2 different assays. The first assay is just Western blot. So we ground up the lung and analyzed the content of neurofilament. Neurofilament is a specific structure protein for nerves. And then compare the saline control versus the ovalbumin-exposed neonatal mouse at postnatal day 21. So what you can see here is there's twice as much neurofilament in the lung in this age. And then we followed up with immunohistochemistry just to observe where these nerves are. So as predicted, these nerves are mostly surrounding the airway smooth muscle, which is heavily innervated in a normal condition. And then upon the ovalbumin exposure, this innervation is significantly elevated in this neonatal model. And then changes in airway smooth muscle, innervation is persistent in this particular model as analyzed by another marker, CGRP. This labels the sensory afferent, and at this recovery phase, we still see a lot more sensory afferents in this lung. So we then went on to the adult mouse model. Just to remind you, this model does not develop chronic airway hyperreactivity. And then what we found is the ovalbumin exposure in the adult model failed to induce airway hyperinnervation. This is the Western blots, and then this is the measurement. So these results told us there's a striking differences in terms of how the airway respond to the insult. So the neonatal window, somehow the lung innervation is completely remodeled, and this remodeling is persistent. However, in the adult model, this neuroplasticity never occurs. So the question is, does increased airway innervation after early life allergen exposure link to persistent airway hyperreactivity? This is the question. The reason why we are interested in smooth muscle innervation and how that linked to smooth muscle function is based on the crosstalk between nerves and the tissue. So the crosstalk between nerve and the tissue is very important, not only for the nerve, but also for the tissue function. So I want to give you 2 examples to highlight this importance of the crosstalk. One is from my own study. The gene that's knocked out in this particular scenario is not important. What I want to show you is a homebound staining of the esophagus innervation. So in this particular knockout, you have same amount of neurons in the esophagus. The only thing that's missing is this dedicated, intricate innervation pattern that's much reduced compared to the heterozygous control. What happened to this muscle is the muscle doesn't contract properly. Eventually, the mice always have food stuck in the esophagus because the peristalsis is compromised. And eventually they die of pneumonia because the food gets coughed out and inhaled back to the lung. So you may say, oh, this is a developmental phenotype. Then I want to give you another case report. This is adult patient. He came to the, this is a paper published on New England Journal of Medicine. It's a case study. So what happened is, this is a patient, he's an adult patient, 45 years old. He has a tumor grow on the right side of his neck. So he went to the surgery. The surgeon accidentally severed the hydroglossal nerve that innervated part of the tongue. So the patient started to feel weakness of the tongue muscle within 7 days. So then the next week, he went in for checkup and have a CT. So basically you can see here is that the side that's denervated, the muscle become completely atrophic. There's no more muscle left on this side of the tongue. So I guess I want to use these 2 examples to show you how important the communication between nerves and target tissue are. And the nerve signal can regulate a lot of phenotypes of the target tissues. So with that question, so this is basically go back to our original question. Does changes in smooth muscle innervation affect the smooth muscle phenotype in this particular neonatal window? So before we can answer that question, I want us we have to know how the lung normally is innervated. So it is known during the development of nervous system, there's a group of growth factors called the neurotrophic factors that are very, very important for establishing nerve and the target interaction. So for example, there's a target A. The target A secretes a specific kind of neurotrophic factor. There's an axon that expresses the specific receptor for this neurotrophic factor. So this axon sends the gradient of this neurotrophic factor, therefore establish the connection. So for another example, there's a target B. They secrete a different neurotrophic factor, and the neurons that specifically express this neurotrophic receptor will go into that direction and establish a connection. So this is how the lung normally is innervated. So the lung is normally innervated by a lot of neurons located outside of the lung. Most of the neuron cell bodies are located in nodose ganglion and the brainstem. They send out axons, travel along the vagus nerve, and get into the lung. And the majority of the innervation ends in the smooth muscle and another tissue called the neuroendocrine cells. So this is the cartoon, and this is the true staining of the TrkB1, which is a neurotubulin marker for nerves, and how this looks like in a whole mount prep. So this is the basically want to show you, this is the trachea, this is the esophagus, and this is the vagus nerve that travel between the groove of these two organs, and then send out multiple branches, get into the lung, and innervate the tissue. So we did a lot of work initially trying to understand which neurotrophic factor is heavily expressed during embryonic development in the lung as well as postnatal development. We quickly nailed down to two important neurotrophic factors. One is called the brain-derived neurotrophic factor, called the BDNF. Another is neurotrophic factor 4. We showed previously both neurotrophic factors are expressed by the airway smooth muscle during development, both in the embryonic stage as well as in the postnatal growth phase. And then they bind to a same receptor called the tyrosine receptor B that's expressed only by the axons that innervate the airway. We believe that's how this airway smooth muscle become innervated. In our study, we traditionally use a knockout animal where the BDNF or NT4 is missing in the whole body, therefore to disrupt this innervation. Another approach we use to disrupt the airway smooth muscle innervation is to use a different allele of the TrkB. So in this particular allele, there's a point mutation in the ATP binding pocket of this kinase. Therefore, you can inhibit this kinase specifically in a very timely controlled manner by a small molecule called the 1-NN-PP1. So if you give the mouse in drinking water this small molecule inhibitor, the TrkB activity carrying this particular mutation will be inhibited, but the endogenous TrkB allele will not be affected. So I want to introduce to you a little bit more about this neurotrophic family. So this family have 4 members, including NGF, NT3, NT4, and the BDNF. I already told you BDNF NT4 binds to the same tyrosine kinase receptor B, while the other 2 binds to a different type of receptors. So I want to show you how these neurotrophin deficient mouse look like. So this is the whole mount staining again, using the TrkB1 antibody to show you the extensive innervation pattern of the axons during embryogenesis. This is a whole mount staining of the left lobe at E14. So you can see the nerves travel along the airway and then branches beautifully and forming very intricate network with the smooth muscle. If you remove the BDNF, which is expressed in the smooth muscle, the number of axons as well as the length of axons is greatly reduced. So similarly, if you remove neurotrophin 4, we found a very dramatic postnatal innervation defects. So neurotrophin 4 turned out to be predominantly postnatally expressed in the lung, while BDNF is a predominantly embryonic neurotrophin. So if you look at the time course of the BDNF NT4 expression, you will notice the BDNF decreased postnatally very dramatically, while the neurotrophin 4 increases postnatally. And this follows very well with the peak of postnatal innervation at postnatal day 14. So this leads us to speculate maybe NT4 is the key postnatal neurotrophin for smooth muscle development. So this is basically show you, these are our hypothesis turned out to be true. So if you don't have NT4, this is postnatal day 21, this very extensive innervation network along the smooth muscle is greatly reduced. Similarly, if you block the TrkB signaling postnatally by giving the mother the drinking water with this small molecule inhibitor, you also similarly blocked the airway smooth muscle innervation postnatally. So to further illustrate that point, we also ran the Western blots to analyze the content on neurofilament. Again, this is a specific marker for the nerves, and you would appreciate in NT4 knockout animal, there's a great reduction compared to the wild type. And if you block the TrkB signaling, in this case, the homozygous TrkB mutant allele, you lose this innervation as well. So just to summarize what we learned, how normally the airway smooth muscle is innervated, is the developing airway smooth muscle express BDNF during embryonic developmental stage, while smooth muscle in the postnatal growth phase express NT4, and then both neurotrophins bind to the tyrosine kinase B receptor on the nerves, thereby establish the innervation. So when we discovered these two neurotrophins, we realized very quickly neurotrophins are involved to some extent, by the clinical reports, are associated with asthma. So I want to give you a few reports that demonstrate the potential connection between neurotrophin abnormality with the asthma risk factor or asthma severity. So this is a first report showing that NGF, which is the same family member within the neurotrophin family, is highly upregulated during postnatal growth in response to ozone, which is a risk factor for asthma in young children. And then similarly, the neurotrophin is also highly upregulated this is in the bronchial lavage fluid in children that are infected with RSV. And then finally, there's a clinical report showing levels of serum levels of neurotrophin 3 and neurotrophin 4 are positively associated with asthma severity in children. So this leads us to speculate maybe neurotrophin and how a smooth muscle become innervated truly play a role in the asthma pathogenesis. So with that thought in mind, we go back to look at how this early life allergen exposure changes airway smooth muscle innervation. This is just to remind you what we found in this neonatal model. We found that the ovalbumin exposure in this neonatal model highly upregulates the airway smooth muscle innervation. Because we know now which neurotrophins are involved, so we went back to examine which neurotrophin expression became deregulated with ovalbumin challenges during this time. So what we found is the neurotrophin 4, which is normally required for smooth muscle innervation during this time, is heavily increased with ovalbumin exposure. This is consistent with an increased tyrosine kinase B reactivity at this time. So what do we believe is happening during this neonatal model is that ovalbumin exposure increases the NT4 expression that leads to hyperinnervated airway smooth muscle, and then this nerve may affect the smooth muscle phenotype. This is our working hypothesis. So to prove that point, we utilize the same ovalbumin exposure regimen, but in this case, in addition to the wild-type mice, we included 2 more animals. This one is the one deficient in NT4, therefore will block the allergen-induced airway hyperinnervation by removing this critical factor. And then the other one is the tyrosine kinase B mutated mice, where we can give this small molecule inhibitor during the challenging phase. So what I want to show you here is the NT4 deficient animal normally have reduced neurofilament content as compared to the saline control. The most importantly, these mice also show resistance to allergen-induced hyperinnervation, as you can see here. This is ovalbumin-exposed NT4 knockout mice. They no longer have the airway smooth muscle hyperinnervation compared to the overexposed wild-type mice. Similarly, if you give the small molecule inhibitor to block the tyrosine kinase B signaling in the nerves, that also blocks the allergen-induced airway hyperinnervation. So with this, after confirming we successfully blocked the allergen-induced airway smooth muscle hyperinnervation, we went back to look at how the muscle phenotype is in this neonatal model. So what I want to show you here is, if you look at this airway hyperreactivity measurement, the only condition that shows ovalbumin-induced airway hyperreactivity is the wild-type mice. So this is the wild-type mice exposed to ova, and again, this is the wild-type mice again exposed to ova. If you block the tyrosine kinase or if you remove the ligand, in both cases, the mouse no longer develop airway hyperreactivity. And then the mouse just never developed airway hyperreactivity compared to the wild-type mouse, where this airway hyperreactivity phenotype is persistent. So the model we came up here is, what we believe is normally every smooth muscle expresses NT4. Upon early life allergen exposure, the NT4 level is increased. That hyperactivates the nerve that expresses the tyrosine kinase B, leading to hyperinnervation of the airway smooth muscle, the result in phenotypic change in the airway smooth muscle, therefore leading to persistent airway hyperreactivity. If you block these critical neurotrophins, you don't have these changes in airway smooth muscle innervation, and therefore the airway smooth muscle phenotype stay the same. So of course, there are many, many remaining questions. So this is not an ongoing study. We're trying to answer the three very different questions. The first question, of course, is what is the signal that comes from nerve and then instruct the muscle to become a different type of muscle? And then if we identify this neural signal, what is the molecular mechanism that changes the smooth muscle phenotypes? And then this is the aspect of research we put a lot of energy on, because we felt that the asthma field needs a little bit more new approaches to study an asthma phenotype, and I will tell you why. So let's first focus on our effort to develop some new approaches to study airway smooth muscle phenotypes. So first one we developed is a mouse model that allow you to isolate the primary smooth muscle cells. The reason why we became very unhappy with the smooth muscle cell line is the phenotype changed dramatically in culture dish. So we believe having a way of isolating the primary smooth muscle cells will give us a way or an approach to directly interrogate the genetic changes in the smooth muscle cell compartment, and therefore will allow us to identify new genes or new pathways involved in the smooth muscle abnormalities. So these mouse take advantage of two lines. The first line is the smooth muscle GLP transgenic line. In this mouse line, the smooth muscle express GLP in both airway smooth muscle compartment as well as the vascular smooth muscle compartment. And then the other mouse cell line expresses DS-RED under a proteoglycan gene called the NG2 promoter. So this particular red fluorescent marker is only expressed in the vascular smooth muscle. So as a result, if you combine these two alleles, you get uniquely GLP positive smooth muscle and a double positive vascular smooth muscle. So utilizing these two colors, you will be able to isolate, this is the double positive compartment by cell sorting. This is the vascular smooth muscle. And then if you isolate the singly GLP compartment, this is the bronchial smooth muscle. So we did a lot of work using this animal model, published a list of genes that are highly regulated in the mouse model with albumin challenges that tell us many things. The first thing we've noticed from this knockout is the muscle is actually an active player in the inflammation. The muscle expresses a lot of cytokines and chemokines. And then second is there's a lot of ion channels that are altered in this particular compartment. So we're actively pursuing which genes that are become deregulated with the allergen exposure plays a role in the smooth muscle reactivity. So the other approach is how can we measure the single cell contractility? So this measurement comes to play when we met a very, very, very important of our collaborator, Dr. Kushner in Brest, Israel. He is here today. So when we have the single cell isolated from the mouse model, we wanted to know whether there is an intrinsic change of the single cell phenotype. To do that, we used the technology very polished by Dr. Kushner. This technology is called a traction map. So this technology takes advantage of very deformable soft gel with a lot of small fluorescent beads embedded. So you could imagine if you put a force on the top of this gel, depending on how the force is delivered, the beads movement and the deformation will be different. So imagine this is a circular cylinder pressed in the middle. You can see the beads move towards the center. If this is not a cylinder, this is a rectangle, the beads movement will be very different. Similarly, basically what you can do is you can measure the deformation, the extended deformation, as well as the direction of the deformation to interpret the cell contractility. So this is what Dr. Kushner did for us. So when we isolate the single smooth muscle cells from the mouse that are exposed to saline or exposed to albumin, or in the wild type or in the NT4 knockout background, he's able to tell us how much forces individual cells produce using his method. So every single dots represent one cell, one measurement. As you would appreciate, in a wild type animal, the albumin exposure changes the tone of the cell. The cells becomes hypercontractile. If you don't have this gene, NT4, again, this gene controls the smooth muscle innervation. This albumin-induced hypercontractile phenotype no longer happening. So I think this is the proof of principle. The nerve does talk with the smooth muscle, and as a result, the smooth muscle phenotype change. So using the same approach, we also went back to the mouse that had been sitting in a cage for 5 weeks. These mouse were originally exposed to albumin, but now they are inflammation-free, but still develop airway hyperreactivity. So again, using these methods, we can measure the cell surface, which is not different between saline exposed versus albumin exposed. However, the contractility in this persistent model is still present. So with this study, we basically at this level, we have a cell, we can isolate the cells, we can also interpret the gene expression, and we can measure the single cell reactivity. And we also have shown some data using a whole lung measurement. So this is the whole flex event. You can measure the cell, smooth muscle cell contractility as a whole to the as a whole. However, both approaches have caveats. The first one with the cell is the cell change phenotype in culture, so it makes you uneasy in terms of what the phenotype means in vivo. However, if you use the whole lung measurement, you cannot interpret it at a single cell level how this phenotype is changed. So what we decided to do is using an intermediate step. So this is not a new technology, but we're trying to elaborate this technology to make it more adaptable for smooth muscle research in asthma. So this is a mouse lung, and we also have quite a bit of study now with the human lung. So what you can do is, just like brain slices, you can collect lifelong tissue in the median. You can keep it in culture for mouse is about 7 days. For human, you can easily do cultures for 2 weeks. So what you can do is you can put in a stimulus to induce the contraction, and you can measure the luminal size of this airway to interpret the reactivity of the cell in response to this stimulus. And if you wash it off, the airway lumen opens up. And I have a video with the human cells. So this is just to show you this is a human airway slices. They are highly variable, very variable, and you can basically stimulate the cells with the stimulus, and you can basically measure the dynamics of the airway lumen shrinking. So the other way we're trying to combine the lung slices is to do live imaging. So what we can do is we can load the calcium-sensitive dye. So what you can do is you can load the calcium-sensitive dye, and then as a result, you can measure how the cell respond to different stimulus by the calcium level. So calcium is a very critical mechanism that controls the smooth muscle contraction. So I want to show you another video again. In this particular case, is a human's airway. So what you are seeing here is the normal calcium dynamics, and then this is the minute you add histamine, which leads to smooth muscle contraction and calcium entry, you have a flash of the increase of a calcium signal as well as the increase of the calcium oscillation levels. So these are the tools we're trying to develop in the lab. And then, but the question still remains, what is the nerve-derived signal that regulates the smooth muscle contractility? So we know the nerve is, the airway is heavily innervated by predominant 2 types of nerves. The first type is the sensory nerve that can be measured by this marker, CGRP. Another type of nerve is the parasympathetic innervation, which can be measured by a marker. This is an acetylcholine marker, VACHT. So if you measure these two markers, what we found is in this neonatal model, the sensory innervation is not changed with the volume exposure. However, there's a great deal of increase in the parasympathetic cholinergic innervation to the airway smooth muscle. So we believe maybe the cholinergic innervation and the chronic exposure to higher level of acetylcholine may lead to the smooth muscle phenotype change. This is something we are actively pursuing now. So the molecular mechanism underneath our phenotype, we believe, is enhanced cholinergic inputs cause inflammation independent by contraction-induced airway remodeling, which in turn leads to airway smooth muscle hyperreactivity. We don't have much evidence to support this mechanism, but I do want to cite some published data. One is in human, another is in mouse models, to prove this mechanism may be at play in our scenario. So the first paper from human that shows acetylcholine can induce airway remodeling is a clinical case study. So this study was published in 2011. So what they did, this group of people did, is they recruited atopic patient groups. And then they divided into two different groups. One group received the cockroach allergen to induce airway inflammation as well as airway hyperreactivity. Another group received only methacholine. And then they compared these two groups at day 8 to look at the airway function. So what they conclude here is bronchial constriction without additional inflammation induces airway remodeling in patients in asthma. So basically, the methacholine has a similar impact on the lung function for these patients, similar to the allergen. So the other evidence in support of our mechanism come from a study published in 2014. So in this particular study, the authors uses a mouse model in which the muscarinic receptor 3, which is heavily expressed in the airway smooth muscle, is disrupted. So this mouse muscle does not respond to acetylcholine. So what they found is, in using the same ovalbumin model, what they found is M3 receptor knockout animal do not develop airway remodeling. So the markers they used is the airway smooth muscle to show the airway smooth muscle thickening, as well as the collagen 1, which is one of the major components in the matrix that can impact on the smooth muscle contraction. So based on these findings, we hypothesize what happened in the neonatal age is the insult in the environment changes how this airway smooth muscle becomes innervated. The hyperinnervated smooth muscle receive an overdosed acetylcholine that leads to chronic airway smooth muscle remodeling and then leads to the persistent airway hyperreactivity. So this is the direction we're actively pursuing. So I guess I will end my talk with acknowledgement. I want to acknowledge the lab. Basically, this is my lab here, as well as a number of very valuable collaborators. Among them, Rama is the key. He's the reason why we can see the smooth muscle phenotype. And then I want to thank Dr. Fine for giving us the smart GLP animal that facilitate the smooth muscle isolation. I also want to thank Levy Group for giving us the support and ideas about asthma. Gina gave us cells, the cells that can differentiate into different kinds of epithelial cells for our study with cell model. And Ivan is a physician who gave us the healthy human donor lungs. So we can start to use what we learned in mouse to look at the human smooth muscle. And I want to thank Michael Sanderson for teaching us how to do the calcium images. And then I would be very glad to take questions.
Thank you very much. That was terrific. And thank you for opening up this whole new world of thinking about airway hyper-responsiveness. So we welcome questions from the audience here or from those who submit them online. And maybe I could ask just quickly, you taught us that denervation would lead to muscle atrophy and loss of muscle. Is there evidence that hyperinnervation leads to increased muscle mass or hypertrophy?
So the tongue muscle is a skeletal muscle, so it's very different from the smooth muscle. I think in the skeletal muscle field, there's not a direct evidence to indicate if you have a hyperinnervated muscle, you get more muscle mass.
What do we know about physiologically what induces the neurotrophin family in muscle?
So how it's regulated? This is a good question. So the study.
Can you repeat the question? Sorry.
Okay, so the question has to do with how the neurotrophin become deregulated in the Waldman condition, right? So so this is an ongoing study in the lab. We actually discovered the muscle itself doesn't contribute to this process. It's the inflammation that brings in the extra neurotrophins. So this builds a very nice story where the nerve crosstalk with the inflammation actually is the drive for this abnormal smooth muscle innervation.
Can I maybe ask another question? We focused on vagal innervation of airways. Is there any other neural pathway? I vaguely remember the non-adrenergic, non-cholinergic pathway that people were talking about in humans. Do we know of any other pathways other than through the vagus that might innervate airway smooth muscle?
So the question has to do with what kind of type of innervation is present in the lung. So in addition to the vagus nerve, another source of innervation comes from the dorsal root ganglion. So this provides a lot of sensory afferents as well as some of your non-cholinergic, non-adrenergic nerves.
Great. Well, thank you very much. Thank you all for your participation, and we look forward to seeing you at the next Asthma Grand Rounds. Thank you.
Thank you.